Okay, so this is more on matrix multiplication, and then we're going to get into what we call matrix algebra, which is going to be going deeper into matrices. Um, First thing we have here is two matrices, x squared, 2y. Yes, of course, we've introduced variables. 2y, 2, 1, and x multiplied by the matrix 1, 5, 3, 7. And we know that this equals A, B, 4, 4, C, and 33. And it tells me to find the value of A. Well, to get A, I'm going to multiply. First thing I should do is check that I can multiply these matrices. Fairly clearly, I should be able to. Okay, if they gave it to me like this, I should be able to. 3 by 3, 2 times a 2 by 2. And that gives me a 3 by 2, which, hey, ever so handy. I can see that that gives me this, a 3 by 2. So to multiply my matrices, I'm going to row 1 time of matrix 1 times column 1 of matrix 2. So that's x squared times 1. I'm just going to put this in the matrix. X squared times 1 plus 2y times 3 is 6y. Here, I'm looking at row 2 times column 1. So that's 1 times y plus 3 times 2. That's plus 6. And then row 3 of the matrix is 1 times 1 is 1 plus x times 3, so 1 plus 3x. Now we're looking at column 2, where I'm going to take, again, row 1, column 2, x squared and 2y times 5 and 7. So x squared is 5x squared plus 14y. That's 2y times 7. Row 2 then is y plus, no, 5y plus, because that's y times 5, and 2 times 7 is plus 14. And then finally, 1 times 5 is 5 plus 7x. So I know that these are equal. It only asks me for A, so I don't need to worry about getting everything here. But I do need to get X and Y. So right here, I'm going to line up. Here I've got an equation that'll get me X. Here I've got an equation that will get me Y. So that's probably the easier one. 5y plus 14 equals 4. I'm going to solve for y. And I get 5y equals, oops, I subtract 14, not 4. 4 would probably work, but 14 will work better. So y equals -2. Okay. And then I will take my x's and write an equation. So I'll divide by 7 and get x equals 4. To get a, I know that x squared plus 6y equals a. Again, that's because I'm lining up my places. Upper left, or 1, 1 equals 1, 1 in the other matrix. And I'll just plug in my x and y. That's 16 plus negative 12, a equals 4. Yes, that's a bunch of work. Yes, if you have matrices with all numbers, use your calculator, do it the easy way to multiply. But you do need to be able to do these without. Okay, I'm gonna look at one more example and then I'm gonna have you do a couple problems. So, example 4 in your textbook says, in 1 month, factory A produced 452 wallets and shipped 270 of them. Factory B produced 720 wallets and shipped 514. Write a 2x2 matrix where each row represents one of the factories. So we're going to have A and B, and this is going to look in a matrix, and this is going to be produced and shipped. So A was 452 wallets, and it shipped 270. Usually you don't put labels on the outside of a matrix, but I think that's a little easier. Factory B produced 720 and shipped 514. So that makes it clear where the numbers in the matrix come from. It costs each factory $12.74 to produce one wallet and $2.39 to ship it. Write a matrix that represents the amount of money spent by each factory on production and shipping in 1 month. So here I've got a 2x2. In order for this to work, I must have a 2 here. They gave me 2 numbers, so that means it's got to be a 2x1. So my production was 1274. I want to make sure I'm multiplying 1274 by the first one and 239. So it does have to be in this order because 1274 is going to multiply by the number of wallets produced, 239 by the number shipped. And I'm going to pop over to my calculator to put this in because I don't feel like multiplying it by hand. And I need to use a calculator anyways. So here is my TI Inspire. To enter these, I'm just going to do the 2x2 is really nice on this one. 452, 270. I kind of recommend the order I'm going in because I think it's faster going through the arrows. And then here I've got a nice 2x1 that I can use directly too. So this ends up being real quick. And my answer is 640.03.78 and 10,401.7. So the total shipping cost and production can be found using this matrix multiplication. Okay, so this is the cost. The top one is the cost for factory A. The bottom is the cost for factory B. It is not shipping and production or production and shipping. It is factory A here on top and factory B on bottom. Okay, we're going to pause the video for a second, and you guys are going to do the 4 questions at the end of 14 or 1.14.3. So that's 1.14.3. Okay, before you do this next part, this is what we call matrix algebra, and this is going to get heavy into theoretical math in what's known as linear algebra. This will lead Thursday into a proof that I did in abstract algebra. It's gonna get hard and conceptually hard real fast. Okay, so we're gonna start with something called the identity. So identity, and we're going to talk about additive identity for regular addition and multiplication first. Identity means whenever I use whatever operation, whether it's addition, multiplication, those are the two we'll focus on, could be subtraction or division as well. But whenever I use this operation, it doesn't change anything. So with adding, the additive identity is 0. And when I add 0 to something, it's just the same thing. We don't usually think about this when we're, adding 0 in first grade or, you know, later on. You don't think about it much until later on and you start getting into the theory of why math works. Okay? The multiplicative identity, think about what I multiply by, and it doesn't change the number. We've talked about this one several times. That's where the clever name for 1 comes in. The multiplicative identity is 1. So if I'm talking about matrices, and we're just going to use a 2 by 2 because that's pretty easy. The additive identity is the 0 matrix. The one we're going to use the most, the multiplicative, is this. And if I get bigger, it's just this 1 down the diagonal of the matrix. But it has to be that diagonal. It's not the diagonal the other way. And so those of you that did reduced row echelon form last year were trying to get functionally to this. And we're going to call this one I. Okay? This is the identity matrix. This is what we're trying to get to. Another thing we're going to talk about is inverses. When we're talking about basic addition, the inverse operation of A is subtraction. The key to inverses is they give me the identity. With inverse operation of multiplication is division or multiplying by the reciprocal, which is how we're going to really want to start thinking about it. A times 1 over A. A is over 1, so this is A over A, which equals 1. That's the identity. Inverses give me the identity. If I'm talking about matrices, A times the notation for A inverse is A negative 1 is going to give me the identity matrix. So no matter what size matrix, it's going to look like this one, depending on the size, but with this 1 down the diagonal. Okay? Couple other things we need to note. The commutative property. And for regular addition and multiplication, this applies. A plus B equals B plus A. I can switch the order. AB equals BA. For matrices, A plus B does equal B plus A. Remember, to add matrices, they must be the same order for both. But multiplying, AB does not necessarily, and usually does not, equal BA. Even if the orders work. So sometimes we had, I think I showed this yesterday, 3 by 2 times a 2 by 4, and show that example. And that would work and give me a 3 by 4. But clearly a 2 by 4 cannot multiply with a 3 by 4 as the insides don't match. But even with 2 by 2 and 3 by 3, that does not work most of the time. There are cases where it would work. I could come up with a special matrices where A times B would equal B times A. The associative property actually, let's go to a new page for this. The associative property okay, this is definitely going to work. So with addition, it's A plus B plus C equals A plus, I can add B and C first before I add it to A. That also holds true for matrices. I'm using capital letters here for matrices. And it works for addition, or for multiplication. I can multiply B times C first. It actually works for matrix multiplication as well. Oops, A can be out here. So I can change the grouping in which order I multiply. Cannot change the order they exist in. It needs to become A times the product of BC. So I need to multiply A first. I'll multiply BC and get something. Maybe we'll call it X. But then A still needs to be on the left for multiplication. Okay. So we're going to talk about left and right multiplication coming up. So A plus B squared. We know when we square a binomial, we need to write it out FOIL. And you might know the shortcut for this, but you cannot use it for matrices. Now, if I knew matrix A and B, I'd just add them together and then square it. But if I don't, I'm going to FOIL. The order these come in matters. Usually I do not take that into account, but A times A is A squared. A times B is AB. Which term? So if you FOIL backwards, if you do this, that's fine. But the order that I put these in, the next one, so I did FOIL, I did outside A times A, and then I'll erase this and draw it in. So here I did A times A is the first one. A times B is the second one. The third one, BA, and then B squared. So the third one becomes really important to pay attention to the order. B is on the left here, so that produces BA. Left multiplying and right multiplying is different in matrices. And this is my result. AB and BA are not the same, so I cannot combine like terms. My final answer is A squared plus AB plus BA plus B squared. You can switch the order of the terms, that's fine. But you cannot make them different. Okay. So again, I'm going to FOIL. I is the identity matrix. I don't know its dimensions. But what I do know is that it's like this along the middle. So 3i is actually not this, and it won't, the identity times the identity stays as I. But this does not. So again, I'm going to FOIL here because 3i is not the identity matrix. Oops, like that. So, no, I wrote that wrong. I will FOIL, and I should write it out like I'm going to FOIL. 3i plus a. So 3i times 3i is 9i squared. This is an identity matrix. Don't mistake this for a small I. 3i times a is plus 3ia. Okay. I should close those parentheses. A times 3i is plus a times 3i. And finally, a times a is plus a squared. Now, I can be simplified. And scalar multiplication by a, so I times I is just I, which is 1. The identity matrix does not change anything. So 9i squared is 9. 3 times I times a is 3a. Because I does not change anything, it's the identity. A times 3. Now, multiplication of matrices is not commutative, but a scalar times a matrix actually is commutative. So 3a is the same as a3. So 3a plus 3a is 6a. Okay. The identity matrix does allow me, however, to add these terms together. Okay. Okay, our next example is going to ask me to show you that this equals this. I will always be the identity matrix. A, B, and C, basically any other matrix letter for the most part, is going to be open, okay, to any matrix. So I'm just going to work here on the one on the left. And I'm going to start by distributing. AB plus AC equals A. I'm going to set it, my goal is to get over to here. Okay. So I have a 0 over there, so I'm going to move my A. I can subtract matrices or, add the opposites. So I've got A plus B, AB, AC minus A. I know that A times the identity matrix is always just equal to A. So that doesn't change anything, changing the A by itself to an AI. So now I've got these three. And if I factor out my A, I can factor out the A to the left only to the left because the A is on the left on all of these multiplications. That is a completely new thing about matrix algebra that is not common in regular algebra. And there I have shown that. Okay. Now we're going to talk about the inverse of a 2 by 2 matrix. Okay. Finding inverse of higher order, we're going to do with the calculator. It gets real messy real fast. Now, a 2 by 2 matrix I'm going to say it looks like this. And there's something called the determinant. And the determinant is equal to AD minus BC. Okay? We write that as determinant of A. And that, in the case of, is AD minus BC. The inverse is 1 divided by the determinant. And that's, the determinant is a single number, it's a scalar. Multiplied by this matrix. We switch A and D, we take B and C, and we make them negative. And that's the inverse matrix. So if I assign matrix A to this, 1, 5, 3, negative 2, A inverse is 1 over 1 times negative 2 minus 5 times 3. Then I multiply that by a switch D and A and negate B and C. This is negative 17, 1 over negative 17. And then I'll multiply that by the whole matrix to give me a final matrix that's a scalar. Negative 1/17 times 2 is 2/17, 5/17, 3/17, and negative 1/17. Okay, so that is my inverse matrix. I'm now going to show that A times A inverse equals I, and we're going to do it backwards too, because they should both equal I. So A times A inverse has to equal the identity matrix. Remember, that's the ones down the diagonal. A inverse A also must equal I. Okay. Inverses are commutative in matrix multiplication. The other ones are not. So that's 1, 5, 3, negative 2 times 2/17, 5/17, 3/17, and negative 1/17. And I'm going to do this by hand just because. So the result, row 1, 1 times 2/17 times column 1, 5 times 3/17 is 15/17, 17/17. Okay? Over here, row 1, column 2, 5 times 5/17. No, 1 times 5/17 is 5/17. 5 times negative 1/17 is negative 5/17. 5/17 plus negative 5/17 is 0. Row 2 times column 1, 3 times 2/17 is 6/17. -2 times 3/17 is -6/17. Those add to 0. 3 times 5/17 is 15/17. -2 times -1/17 is 2/17. 15/17 plus 2/17 is 17/17, or 1. That worked out. Now we're going to do the other way around. This one's not in the book, but I'm pretty sure it's going to work. Okay, row 1, column 1. 2/17 times 1. 5/17 times 3. That's what we got. That's 17/17 again. If you're having trouble with this over here, got row 1, 2/17 times 5 plus 5/17 times -2. That's 10/17 plus -10/17 is 0. 3/17 times 1 plus -1/17 times 3 is 0. That's 3/17 minus 3/17. 3/17 times 5 is 15, plus -1/17 times -2 is positive 2/17. 15/17 plus 2/17 is 17/17, or 1. So the inverses do multiply to give me the identity. Okay, a singular matrix means the determinant is 0. Okay. Usually we use A, B, and C. I'm going to use X for this one, capital X. So I'm trying to use them for the other end of the alphabet. Has determinant of X equals 0. So if we ask me, if they give me this A for a matrix, and they say it's a non-singular matrix, that means determinant of A is not equal to 0. So we're going to find what values X cannot equal. X could equal all kinds of values, but it can't equal something. So to do this, I'm going to go 1 over AD, that's X squared times 2, minus BC. Okay. Oh, wait, not 1 over. I'm just doing the determinant, not the part about the inverse. The determinant is just the AD minus BC. It's not the 1 over part. So I'm going to find out what it is. And I know that 0 cannot be equal to this. So 2x squared minus 8. We're going to find where it equals 0 by solving this equation. I'll divide by 2. I get x squared equals 4. And then I'm going to solve this, I will square root both sides. And when I introduce the square root, I must introduce the plus or minus, because positive or -2 squared would give me 4. So what I don't know anything about the value of X, except it is not equal to 2 or -2. Yes, you can write it like this as well. That is fine for this. Okay, if we get a 3 by 3 matrix, We will do the inverse on the calculator. I'm going to show you how to do that on the calculator here in a second. Okay. So the matrix is example 5. I'm just going to enter it in here and let you see it. So to start, I'm going to pick my sizable matrix that defaults to 3 by 3. So in order to not change the size, I'm going to move my cursor to the left. Probably could have just hit enter there. And this is the matrix they give me. No, not 0.2, -2. To do an inverse, the notation is to the -1 power. It doesn't mean the same thing as the -1 power, but the calculator will interpret this as inverse. There's my inverse matrix. 2/9, 1/3, -10/9, 1, 1, -5, -4/9, -2/3, 29/9. Okay, we're going to talk about, in general, how to solve a matrix equation. Matrix A times matrix X equals matrix B. Okay. In order to solve this, you'd usually divide by A to get X by itself. Well, with matrices, there is no matrix division. There is multiplying by the inverse, however. So what I'm going to do is AX, and I'm going to multiply both sides by A inverse. Okay. So over here, I've got B. The trick, though, is I multiplied the left side of the equation on the left by A inverse, which means I have to multiply it on the left. This is not equal to B A inverse. That does not work. Order matters in matrix multiplication. These two I can group together and call the identity, because we know the inverse times the inverse of a matrix times matrix is the identity matrix. The identity times anything is just that something. So X is equal to A inverse times B. We're going to talk about why this works with orders of matrices. Okay, this only works if A has an order it's a square matrix. That means the columns and the rows are the same. You can't get the inverse of a non-square matrix. Sorry, that's unfortunate. But in order for AX to work, X must then have dimensions n by something else. It could be n by n, but it could be anything. M could be equal to n. These inside dimensions must match, and B must then have dimensions n by m. A inverse must also be n by n, because the inverse of A. That was multiplication there. X is n by m. The key multiplying this A inverse on the left. N by n. And we end up with these two dimensions, n by n, which is what we had when we had X equals A inverse B. Okay. If I tried B times A inverse, I'd have n by m times n by n, And if m is not equal to n, this would not work. Okay. So that's it for today. We'll go more into this on Thursday.